Welcome and thank you for joining us for this webinar presentation. We are the Homeland Defense and Security Information Analysis Center, or HDIAC, one of three IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. HDIAC serves as one of the premier information research partners and curators of technology advancements and trends for the Homeland Defense and Security community. As such, our organization supports those working in the Homeland Defense and Security domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. With an understanding of the Homeland Defense and Security DoD research and engineering landscape, we provide research and analysis services. We help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar presentation and that it serves as a catalyst for community collaboration and improved DoD Homeland Defense and Security research.
Good day, everyone. Thank you for joining this webinar presentation. My name is Philip Payne. I am subbing in today as a guest host for the technical lead, Jonathan Clemens of the Homeland Defense and Security Information Analysis Center, or HDI. Before we get started, I'd like to note a couple of administrative items. First, if you are dialed in by phone and would like a copy of the slides, they were posted to the HDIAC webinar announcement. You can go to hdiac.org/webinars and find today's webinar. When you click on it, at the bottom of the announcement, it will say download presentation. Second, all participants are muted, but feel free to chat using the attendee chat window on the lower right-hand side of the webinar screen. You can use that to chat with each other, and I'll be monitoring that chat as well. However, if you'd like to pose a question for the Q&A session at the end, please click the three dots labeled More/Panel Options to bring up the Q&A window as part of your layout. At the end of the presentation, I'll go over the Q&A. For the benefit of those on the phone, I'll read the questions out loud to the presenter. If you have any technical issues during the presentation, have no fear. The full presentation will be online. Please check back to this HDIAC website. Once the webinar is posted, the GoToWebinar button will take you to the YouTube link. With that said, I'll introduce today's presenter. Dr. Robert Hayes is an associate professor of nuclear engineering at NC State University. He focuses on novel shielding technology, radiological air monitoring, and retrospective dosimetry for nuclear safety, nonproliferation, emergency response, and radiation protection applications. He currently holds a joint faculty appointment with the Savannah River National Laboratory and is associate editor of the Journal of Radiation Physics and Chemistry. He's also a licensed professional engineer in nuclear engineering, certified health physicist through the American Board of Health Physics, and a fellow of American Physical and the Health Physics Societies. He serves on the Advisory Council for Nuclear Security for the Administrator of the Department of Energy's National Nuclear Security Administration. Dr. Hayes?
All right. Today, we get to talk about something completely different and entirely exciting. So to start off with, let me caveat all of the calculations that we're going to be seeing were done with MCMP6, and some of the visualization was done with VizEd. And so at the moment, like pretty much every SMR, commercial SMR that's out there, it's a paper reactor. But let's get into the physics because it's really cool. All right, so to start off with, if I take beryllium and natural uranium, as you can see here on the left, any combination of an infinite system of homogeneous beryllium and natural uranium will never be critical. If you look here at the K infinity for an infinite system, for all combinations of beryllium and natural uranium, you can never have a K effective above 1. In fact, you'd barely get above 0.8 for all possible combinations. And there's just this one combination of beryllium where you get the highest multiplication. Similarly, if you look at water, light water, with natural uranium, you can again never be critical in a homogeneous system. So again, looking at the K infinity as a function of your hydrogen to uranium ratio, you have a place where you get up to almost 0.9 for your K infinity, but you never get above it. And that's for homogeneous systems. So let's look at a unique configuration of heterogeneous situations, specifically slab geometry. So here again is the combination of homogeneous systems. You can see it never gets above 0.9. But if I plot the K infinity for slab geometry, so repeating slabs of water, natural uranium. So if I have an infinite array of slabs of water and uranium, I can get substantially above 0.9. I can get upwards of above 0.95. So even though the homogeneous case can never get above 0.9, the heterogeneous case, if I have slab geometry, can get up above 0.95. And you can see here for the range of the water thicknesses and the ranges of the uranium thicknesses, there's a region up there of maximum multiplication.
Dr.
Again,
Hayes, sorry to interrupt. We're not seeing the slides advance. You
oh
might
dear.
want to go into presentation mode. We can only see the title slide as of right now.
Well, that didn't work in the practice. Can you see it now?
Yeah. Well, yep. It's a lot bigger, and we're on slide 5 right now. Well, actually, you can see you.
Is it advancing forward and backwards?
Yes, correct.
Okay. Well, what I
Yeah,
was
we're good
saying
to go
before,
now. Thank you.
can you see my cursor?
Yes, we can. Yes.
Well, that's just weird. Okay. All right. So what this is what I was talking about here, where the beryllium and the water, they never go critical. Here is where you look at the water for a homogeneous case, and on the right you can see for the slab geometry where there's this region up here of maximum multiplication. So that you get a lot more reactivity if you have the right combination of thicknesses of water and uranium, natural water and uranium metal, natural uranium metal, where you can get a much higher multiplication. You do the same thing with beryllium and something magical happens. You see here on the left, the infinite case where I have homogeneous beryllium and water, and I can barely get up above 0.8 in terms of my K infinity. But if I play that same trick of having slabs of beryllium and natural uranium, then there's a region of the uranium slab thickness and the beryllium slab thickness where I go way up above a K effective or K infinity of unity. In fact, I can get up to a place where it can be prompt critical. I can get up to about 1.09 in terms of the K effective. And there's a range of uranium and beryllium slab thicknesses where that will occur. So if we compare these, so these are the slab configurations mapping out the infinite K infinity for all possible combinations of slab geometries of natural uranium and beryllium and the water and the natural uranium. You can see here that the optimum thickness in the natural uranium beryllium mix, the uranium has a thickness right around 1.2 centimeters. And that also corresponds to right around the range where you get maximum reactivity for the water and the natural uranium configuration of, again, the uranium being about 1.2 centimeters. Now, in that range, the water, it's about 2 centimeters for that optimum thickness. And the beryllium, it's about 12 centimeters thick. And so then that begs the question, can these be combined for a potential power reactor configuration? Because the natural uranium is the same thickness for optimal reactivity in both configurations. So both configurations have a common thickness of natural uranium. So in other words, if you look over here to the right, if I combine those layers, so I go beryllium, natural uranium, light water, natural uranium, beryllium, natural uranium, light water, natural uranium, beryllium, and just keep repeating that, I'm now separating the natural uranium layer between an optimal thickness of water and an optimal thickness of beryllium on each side. I just alternate as you go through. So you have this repeating array, as you can see down here, of what the configuration would look like, where I'm now using a heterogeneous configuration to optimize the reactivity by selecting the appropriate thicknesses of each layer. And so this got this idea was originally published. This was just a hobby that I was doing a long time ago because I'm a nerd. And I published this a long time ago, back when I was working at the waste isolation pilot plant, because I do like these intellectual concepts. And this was whoops. And so that was a long time ago. All right, now let's talk about the physics. How does this happen? How do we get such high levels of reactivity by simply going from a homogeneous case to a heterogeneous case? How does that heterogeneity increase the reactivity so much? So we're going to go through the easiest way to explain this is to go through the four-factor formula. So if everybody remembers, hopefully you do. If not, I'm going to tell you now. The K effective is the number of neutrons at one point in a cycle divided by the number of neutrons in a previous cycle. So if you think of every time that I'm generating a set of neutrons from fission and all the physics that happens as the neutrons go from fission of one generation to the next generation, that's going to be encapsulated in this four-factor formula right here. I'm largely going to ignore the losses from fast and thermal neutrons at the boundary, and we're just going to focus on epsilon p, eta, and f. And so let's walk through those, and then we'll be able to see why this configuration is able to give us this hyperbreeding, this excessive reactivity potential that can then be leveraged and taken advantage of. Whoops. All right, we start off with epsilon, the fast fission factor. Now, in a standard light water reactor that we have today, the fuel is in the form of pins, and these pins are very thin, something like on the order of a centimeter diameter. The fuel has about a centimeter diameter, plus it's got oxygen in there. It's 2 oxygens for every uranium that's going to be in these pins. And so in order to have fast fission, the fission that takes place in this pin, it's got to find, it wants to find another uranium-238 right away, because it's going to be a high energy neutron, and it wants to fission that uranium-238. But it has to do that basically before it interacts with any kind of a moderator. Once it sees that water, if it bounces off of that hydrogen in the water that's between those pins, then on average, it's going to lose half of its energy in a single interaction. And so the fast fission factor is really quite small, because those neutrons, basically, they have to travel up and down the pin and then hit a uranium-235 before they hit an oxygen in order to have a high probability of fast fission. By simply switching over to a slab geometry, where now I've even removed the oxygen, so I'm just using metallic natural uranium, then the solid angle that those neutrons are able to travel and see the natural uranium, the uranium-238, and fission that before they're moderated, before they slow down, is substantially higher by a factor of about 2 pi. So the solid angle, if you remember the definition, that's just basically the fraction of area on a circle that's centered on the point. And when you do this calculation with MCMP, the fast fission factor is approximately 1.09. So that's just huge. That's about 50,000 MPC. So that's a big boost, simply because you're increasing the fast fission probability by a substantial amount, going from basically a linear configuration to a planar configuration, allowing a very large increase in fast fission probability. And I'm not advancing. There we go. All right, P, the resonance escape probability. Now, there's a formula that's given in Schultes and Faw, and you can use this. And when you calculate that value, you do get a higher resonance escape probability if you're using beryllium as opposed to natural water, light water. And what we're seeing here in this picture, and this is semi-log, so the ordinate is linear, is you can see the flux in the beryllium as a function of the K effective. So if you want to get all the way up to the highest K effective, that's greater than 1.08, and this is for the reactor configuration, then you can see that the thermal flux just gets huge compared to what you have when you're subcritical. And the fast spectrum hasn't changed much. And then you can see the resonance region in between here. But when you use this calculation, you find that, again, the resonance escape probability is higher. Let's talk about the physics of this a little bit more. So here's that same graph in the upper right here of the spectrum for different K effective values. And down below, we can see the cross sections, total cross sections for uranium-238 and uranium-235. Now, I've lined them up so that you can see where these resonances for the uranium-238 line up with the spectra. And you can see where the uranium-238 resonances are high, you're getting dips in the actual neutron spectrum that you're seeing in the beryllium. Now, the ordinate, again, is linear, so this actually, it doesn't actually go to zero, but it gets really, really low. And so what's happening with the resonance escape probability is you want the neutrons to get from fast to thermal without having to be absorbed by the uranium-238, because you do want the neutrons to see the uranium-238 right when they're up in the fast region, but while they're being moderated, you don't, because then you're just losing them. The uranium-238 acts like a poison once the neutrons have been scattered to epithermal or slightly higher energies. The uranium-238 will really only fission if you got about a 2 MeV neutron that's coming in there. So you want to avoid these resonances because, again, the uranium will act like a poison, and the 238 will act like a poison. And so that's why you want your resonance escape probability to be increased. The thermal utilization, F. Now, this is an approximation using standard light water reactors for F. So if you do this calculation, you're looking at the macroscopic absorption cross-section for the fuel, and then you're looking at the macroscopic absorption cross-section for the non-fuel, and then the volume elements of both of those. And what ends up happening is that the dominant factor here for this reactor turns out to be in this macroscopic absorption cross-section for the non-fuel, because for the light water, the hydrogen is a poison. It will absorb neutrons. Now, the beryllium will also absorb neutrons, but far, far less. So when I have a much smaller non-fuel absorption cross-section, macroscopic cross-section, my thermal utilization is increased. And so I also get another bump from F. None of these are as big as the fast fission factor, but I do get an increase. So all of these factors so far are increasing. And so my K effective will be larger than what you get for a standard homogeneous or even an LWR. All right, what about eta? You can't really change eta. Once you've got your flux fixed, eta is fixed. And so there's a common paradigm in our discipline that you cannot have breeding in a thermal reactor because eta is not large enough. And that would be true if everything else was the same, but everything else is not the same. And so eta does not prevent breeding in this reactor. What is eta? Eta is the number of fissions per thermal neutron absorbed in the fuel. And you can calculate it by, calculated by this formula for nu, where you're looking at the macroscopic absorption cross-section, fission cross-section for the fuel versus the total macroscopic absorption cross-section for the fuel. And so this number is fixed. Now, it does change, as you see here on the right, as a function of burnup, simply because we're breeding in plutonium-239, and so eta is also a function of the isotope. So eta does increase in this reactor, but initially that's not going to be changed at time t equals 0. However, there is something else that does effectively increase eta, and that's that the beryllium itself has an end-to-end cross-section. So if I have a high energy neutron coming into the beryllium, I can actually fission that beryllium into 2 alphas and it'll spit out 2 neutrons. So I just doubled the number of neutrons when I go in and fission the beryllium. And so what this means is this configuration that we see here actually does increase, and effectively, assuming that this is if you're going to talk about this fissioning effect in the beryllium, and you're going to say, well, where am I going to model that in my K effective? The only place to really put it is to eta. So effectively, it does increase the eta, because there really is no other place to put that in your K effective formula. And so for all intents and purposes, every one of those parameters has been increased if you use this configuration relative to, say, a standard LWR. Now, I did mention that I'm ignoring the thermal non-linkage and the fast non-linkage. And that's because the reactor that was modeled here was really large. And with this large reactor, you're not getting a whole lot of losses out there. Now, you do want to have some kind of a reflector that's out there, and that gives you nominal reflector savings. But to go through the rest of this presentation, we want to remember that the cross section, this was a cube. I modeled this as a big cube because they're slabs. And so this was just a cube. It was very simple. And so along any of the axes through the cube, you're going to get effectively a cosine distribution of the flux. So these big teeth, that's the flux in the beryllium. And then these other ones in between are the natural uranium, which is then straddling the water. And these are not normalized by thicknesses. These are just cell numbers. And so there's no, the width of those has no spatial relevance. It's just telling you the flux in each of the different materials as you're going through the plates, normal to the plates. Okay. If we then go in and do the calculation for the breeding, how much fuel am I making per fuel that I've used? If I'm up to standard reactor temperatures, upwards greater than 500 degrees centigrade, the breeding ratio is 1.55. And so that alone, I think, would justify calling it a hyperbreeder. To my knowledge, there's never been a reactor even conceived of that could even match that level of breeding. The breeding is just huge for this kind of a reactor, which is why the calculations show if you start at a given configuration, it can breed itself into a prompt critical state. Okay, so now let's remember that I was using MCMP to do these calculations, and that the flux is a cosine through the core. Now, if you use MCMP, every time you do a burn-up step, it homogenizes every cell. So even though one of the plates will clearly have a cosine distribution, meaning there's a lot more fission in the center than there is out in the corners, the MCMP will homogenize that. So the way that I went to go ahead and address that was I took the big sphere and I inscribed a sphere inside of that where I separated every plate into two different cells. So the plates on the edge would have just a small piece of the circle of the sphere. The plates in the center would have basically the entire circle touching the edges, and then towards the sides of the reactor, you would have something in between. And so what then you are able to do is you're able to do burnup of the two materials separately. So the center, where you're getting a lot of fission, that's treated as one material, and then the outside, where you're getting less fission, that's being treated as a different material, so that the buildup of fission products and the poisoning effect and the breeding effect are treated with more fidelity by simply separating all of the plates into these two materials. And you could do a lot more if you were to have multiple spheres, but this is all that I did to substantially increase the burnup potential that comes from this reactor. And doing that, we got this result. And so this was published back in 2008. And what you can see is that at a gigawatt, you can get well over 1,000 days. And so all of these are basically giving you the total same burnup. So if you do a higher thermal power, then you get less time. If you do lower thermal power, you get more time. But the key is that something in the range of a few months to many months, the reactivity, the K effective, is going to be up above prompt critical. So you're going to have to do something to prevent that. Otherwise, it's going to disassemble itself. And that's all fine and good. What are the different ways that you can mitigate that? Well, one of the ways to mitigate that, to prevent it from breeding to such a high K effective value, is to insert, rather than natural uranium, use depleted uranium. In other words, lower your enrichment. And I've got a student that's working on this design now. It's the first student that I've had interested in it. And since I don't have funding on it, this was a student that came with his own funding that wanted to do research in this reactor design. And what you can see here is that you can have up to 2 plates in the core and still be able to run this reactor as a power reactor. Or in principle, you could even blend some depleted uranium, or you just use control rods or control plates or something like that. So theoretically, you could actually run this reactor design with some depleted uranium to actually make electricity to prevent it from getting to that level of reactivity once it's breeding in the plutonium. Well, with all of this stuff that's happening, what's going on in the beryllium? If the beryllium has this end-to-end reaction, what about the rest of the materials? So this is a log plot, and you can see for the mass of the beryllium that the creation of lithium and boron is just incredibly small. Now, it's not until you get to the end of burnup where the lithium-7 starts to approach a fraction of a percent. So the different elements that are forming in the beryllium outside of the helium are quite small. And so what we're expecting then is that the dominant effect is going to be the helium creation and the defects created by scatters, by dislocations that are going to be taking place in that beryllium. What about proliferation? Shouldn't we be concerned about a hyperbreeder having proliferation issues? Well, the funny thing is that because it breeds so much, it's going to take any plutonium-239 and start activating it, because the breeding that you get with the uranium-238 is the same kind of basic concepts that happens with the plutonium. So if you map out the different plutonium isotopes as they evolve over time, and then you go and calculate the plutonium grade, you can see that very quickly it literally just exponentially falls off, so that you're not going to get a whole lot of plutonium generation, because it's going to have to stay in the reactor for a very short period of time. So you're not going to generate a whole lot if you want to maintain weapons grade. If you want to get any power from it, it's going to rapidly degrade so that it's no longer weapons grade very, very quickly, far faster than you would for something that's not a breeder, say something that's just like a converter reactor, like a standard LWR. So the publication that we did, we went over a lot of the other non-proliferation aspects. So even if somebody were to try that and they were to say, all right, I don't need to make a whole lot at once, but I'll just run, 100 plates through the reactor and get a small amount of plutonium, there are a lot of passive non-proliferation aspects that one can use. And I did another lecture for the HD IAC on this stuff, and this was in our publication, and this was coupled with the potential for proliferation concerns. There's a lot of passive ways that you can do monitoring for these reactors, and that's what these papers talk about, which we went over in the publication, their most recent publication, in Progress in Nuclear Energy. So that's all fine and good. That's all of the exciting reactor physics. And so if any of you ever had a reactor physics course, I would assume that you've just had your intellectual side quite excited and tickled. What we're doing now is looking at how to use this instead of a large power reactor, is to use it for like a fission battery, a microreactor. And so we're looking at the potential, and we actually did publish some of the preliminary insights on that you could actually do a fission battery using just commercial enrichment. And so with this kind of a configuration, you no longer need HALEU. If you use this configuration, only other people will need HALEU, but this one could actually potentially do fission battery with 5% enriched. And so that's kind of exciting. That you might be able to do that. And then there's also similar applications for SMRs. If you want to do an SMR, you have similar benefit that you could have, in that using just pure natural uranium for an SMR, you don't need to worry about having, for example, the depleted uranium or something like that. Oh, and the other things that we're working on for the fission battery, we got some really novel ideas. They'll be coming out next spring is when we anticipate publishing these, on how to make this in a fission battery with passive safety. So walk away safety, so that if everything fails, there are no phase changes. Literally everything in the core with that design, if you look at the materials that we had, we've got some really novel ideas that we're pursuing that would ensure that if the heat removal capability was removed, it would shut itself down, and it would just get really, really hot, and it would just be expensive, but there would be no phase change. So there's no expectation for any kind of a release under a worst case scenario, which is what you want for a fission battery. But then we also want it to be battle hard, so that it could be used for the military, or more specifically, if it's going to be used out, say in Alaska in the wilderness, you don't want, say, an avalanche or any other natural disaster to cause a release. And so we're coming up with some interesting ways. I won't share those because we haven't published it. And if we want to patent it, I'm going to have to wait until that happens. But we got some really interesting ideas on how to provide this passive walk away safe configuration for this, even though it's got beryllium in it, massive amount of beryllium, but it is a nuclear reactor. All right. So what are the pros and cons? Well, because it's my design, there are no cons. They're just considerations. But I'm biased. This is my design, so that's how I talk about the cons. They're only considerations. So some of the biggest pros for this is that you could potentially, for a power reactor or some larger SMRs, you can use natural uranium. If you get to the smaller designs, a smaller SMR or a fission battery, then you only need 5% enriched uranium. That's kind of impressive. If you're going to do the large power reactor, then potentially you could start using DU. Why that's attractive is that we then would, in principle, be able to turn depleted uranium into electricity. We'd be able to turn what previously has been considered and classified as waste and make that a useful fuel. Things that haven't been looked at, that we haven't published yet, we're doing research in it now, are materials, thermal hydraulics, and optimizations of the design. So we are doing research. As I said, I do have a PhD student that's working on it now. And so that should have been done in a half hour. So there should be plenty of time for questions.
Dr. Hayes, thank you. We do have a very active chat, so I'll step through the questions now. The Q&A session is now officially open. For the benefit of those on the phone, I'll read the questions out loud to the presenter. So I believe the first question that we got in the chat was from Scott. He says, do we still achieve a negative coefficient of reactivity?
Oh my goodness, I can't believe I skipped over that. Oh, thank you so much, Scott. Yeah, what ends up happening is that I actually had an arrow here to remind me. What ends up happening is that if in the power reactor design, if I remove the water, effectively, when I remove the water, I effectively double the uranium thickness, right? Because now I have a void, and if I have a void there, then the uranium is just 2 layers of uranium, and I have just driven the whole thing subcritical. Or the region, wherever I have boiling, it's going to be subcritical because now the uranium thickness is doubled, because I have to keep that uranium thickness right there around 1 centimeter. If I double it up to 2 centimeters, as you can see there, it goes subcritical. And that's the K infinity. So I substantially reduce the reactivity if I remove the water, because I need that neutron buffer between those layers in order to get the optimization effect. So it literally will shut itself down if you have a thermal excursion. Great question. Thank you for that. I missed my own mnemonic. Sorry.
No worries. Next question also from Scott. How do we achieve fission using stable uranium-238 versus conventional uranium-235?
Well, for this reactor, it's predominantly the uranium-235. That's what's actually reacting here, is the uranium-235. The difference with this reactor is that although it's the uranium-235 that's fissioning, it's just a natural enrichment. So I don't need to go through an enrichment process to attain this. This is all with 0.7% uranium, 7.71% uranium. What happens with this configuration, though, is that when I go through and do the burn up, is that the breeding ratio, that 1.55, after a few months, I start to get an increase in the plutonium. And that plutonium, as you might recall, I showed that right here, it has a higher eta. And eta is a factor in the K effective. So this jump in eta eventually will increase my K effective, but until I start to get enough fission products generated, I don't get that, it doesn't start to come back down. I need to start generating enough fission products to take that reactivity back down to near unity. So I hope that answered the question.
Thank you. Next question from Adam. For fuel development, will we just take our yellow cake and be able to stamp sheets of uranium-238, or would we still need to do some sort of chemical enrichment / cleaning before making into planar sheets?
Oh, it's far worse than that. This is pure natural uranium. Yellow cake is U3O8. And so that's not pure uranium. It's pure uranium ore. It's ore that's been purified. in the natural uranium mineral. This is pure natural uranium, which means that it's metal. So you've got to go through the smelting process to convert the yellow cake into a metal.
Thanks. Our next question from Scott. What pressures are required for the 527C at 1.55 to allow for what I suspect would be nucleic boiling?
Yes, I don't remember off the top of my head. It's the same parameters that's assumed for standard PWR. I don't remember what those are off the top of my head. Sorry.
All right. Next question. So we burn fuel from bottom up with control rods. Is it throughout the reactor or other?
So that has not been determined. So we're not currently pursuing the power reactor. We're looking at SMRs and fission batteries. But what was been presented was all passive. It was just allowing the reactor to evolve on its own. So there were no control rods modeled, nor any control sheets. This is just looking at the native design with no other perturbations. And so you could do it in either way. You could do it with boron in the water if you wanted to have some negative reactivity, or gadolinium. You could put that on the fuel. None of those were modeled. So no neutron poisons were modeled outside of just those raw materials: the natural uranium, the light water at natural abundance, and the beryllium.
All right. Our next question from Scott may have been answered in the chat, but I'll ask it here for completeness. He says, having trouble understanding how shutdown and startup is achieved.
So we didn't do modeling in detail for shutdown and startup outside of what you see here. The idea being that you would have some kind of a neutron poison in the reactor when you're assembling everything. You get the water running through it, and then you would slowly remove the poison to start the system up. None of that was modeled. This is a very beginning stage paper reactor. It's had zero funding to date. So you get what you pay for. This is just me doing what I like to do as an academic, using my academic freedom to do the analysis that I like. But the startup is simply assumed that it's controlled in that way, that you then remove the neutron poisons to allow the reactor to start going. And then the terminal ends that you see here is simply where the fission product poisons start to build up to the point where they shut the reactor down naturally. And so that's all that's been modeled at this point. For the startup and shutdown is just what you see here. A lot more to do for sure, but when you're doing it in your spare time as a hobby, that's all you get, except for the student. The student's done a lot of work, and we'll be publishing that. That's going to be coming out in the spring. So a lot of developments there in the spring. It's going to be a lot of explosive numbers of papers compared to the ones that have been published in the past. There'll be a lot that's coming out.
Next question from Abraham. Has anyone considered the property/chemical effects of using a type of refined raw natural perlite to stabilize thermal reactions? It will be more of a neutral thermal material in this project. I'm not sure how much it has been researched.
Could you repeat the question?
Sure. From Abraham, has anyone considered the property/chemical effects of using a type of refined raw natural perlite to stabilize thermal reactions? It will be more of a neutral thermal material in this project. I'm not sure how much it has been researched.
All right, I think I understand what the question is, but I'm going to rephrase it, because if I understand it and I rephrase it, I will be able to answer it. I believe what he's addressing is the fact that when you irradiate uranium metal, it will deform. And that means that even uranium dioxide will deform with burnup, but it's not extreme, so that it'll maintain an envelope inside the cladding. But if you do pure uranium metal, it has a lot more deformation. And I don't know if there are other ideas for that, but we have ideas, and those are the things that we're going to be publishing in the fall, are ways to mitigate that. How can you do this kind of a configuration where you're using metallic uranium or something equivalent that will allow you to get all the benefits that you have from this design, so that you can, again, just use commercial enrichment to do a fission battery. And that's one of the papers that will be coming out in the spring, is how we plan to mitigate that. I think that addresses the question. If not, may need to recalibrate me.
All right, our next question from Eric. If we only use the spherical cross section, what is the minimum viable radius for our SMR?
Well, it depends on it. Read the question again.
If we only use the spherical cross section, what is the minimum viable radius for an SMR?
So it depends on the enrichment. If I go up to 5% enrichment, I don't think I'm really doing much of a spoiler, but if I do up to 5% of enrichment, I can fit it in a transportainer.
All right, our next question from Eric. Does refueling involve plate reordering of full module replacement?
That's what was modeled. Yes, so that it's like in a can-do. You would slide something in while you slide something out. That was what the assumption was. But again, we're no longer working on the power reactor design. Our focus, because that's where, in my opinion, I'm more likely to get funding for future students, is on fission batteries and SMRs.
All right, our next question from Philip. Do the burnup calculations include hydrogen, helium, lithium buildup in the beryllium?
Oh, that is a fantastic question. The answer is yes. But like I said, that has been modeled. And I do have what was, I think, the dominant pieces of elemental distribution. Where'd it go? There it is. What's not shown here is the helium. This is the kind of thing that's going to be coming out in the future for the beryllium. How do we mitigate the helium? We got some really great ideas, because you're going to get a lot of helium, but the other elements that are going to be present, as you can see, are negligible until you get towards the end of life. And the materials analysis is one of the things that I've already had a student make some really impressive progress on. It wasn't me, it was him. He did the analysis.
Thank you. Monitoring the chat and the Q&A, I do not see any other questions at this time. Actually, one just came in from Alan. He says, what are your thoughts and comments on salt reactors like what Bill Gates et al. Are proposing to do? How does this compare to their proposed approach? Pros, cons, relative safety comparisons?
Well, a lot of what Bill Gates has proposed is proprietary, but I love the idea, and I hope everything that they claim is the gospel truth. That would be my preference. So my thoughts are, for all of those other paper reactors, I hope that everything that they claim is empirically unquestionable and will be realized sooner than later.
Thank you. Another question that just came in from Eric. Would this geometry approach work with fusion fission hybrid reactors?
Not so much. If you wanted to combine this with fusion, I'm thinking with a tokamak. I don't really see how I could integrate this into a tokamak in a way that would be potentially useful. I mean, there probably is a way you could combine it. We haven't looked at that at all. It's not on our radar. For me personally, at the moment, I'm just looking at doing research along directions that are likely to get funding, because a lot of people haven't liked this idea. It's extremely revolutionary. A hyper breeder never existed. It's a completely novel concept that has taken a lot of people a while to get used to the concept that you actually could do this, that the physics is good. Kind of characterizes my research history. If you ask me, anyway.
Thank you. Is there anything else coming in? Yes, we just got a brand new question. We got a couple more that just came in, actually. So the next question we have from Aswani. There's a Chinese company, Beta Vault, that makes a nuclear battery with a 50-year lifespan. Is this technology different from that?
Oh yeah. Nuclear batteries are going to be radioisotopic thermoelectric generators. So you're using the Seebeck effect. Kind of, it's like thinking of the easy way to think of it is like a thermocouple in reverse, kind of. so that by having two dissimilar metals that are welded together, if you have a temperature difference between the ends, it creates a potential difference, and you can use that to create an electric current. And so you just need a heat source. That's what NASA uses, like on their rover or any of their satellites that go out into the solar system, where solar panels aren't sufficient. Is you have one of these. It's called an RTG, radioisotopic thermoelectric generator. And so that's just a source of concentrated radioactivity that provides you the heat source to run an RTG. So this is something very different. You basically could use the fission products for that, but usually we don't like using fission products for an RTG because of the gamma. You prefer to use alpha emitters like plutonium-238 is a really good one. Something like that, polonium-210, things like that.
Our next question from Adam. Are you taking any lessons learned from the French breeder reactors or industry in the designs for these?
Not so much, because right now we're still in the initial design stage. And if I go back to our upcoming priorities, it's going to be how can we make this passively walk away safe? So if you just forgot about this thing, it just largely becomes a new geological formation for all intents and purposes until it just erodes away in such a way that it's not going to be. The idea is by that time the chemotoxicity, the heavy element toxicity, becomes comparable or dominant over the radiotoxicity. I mean, that's kind of the goal. So these things are incredibly passive. Theoretically, we would like it to be so hard that you could use it in a battle scenario. So the military could use it because it would be so resistant to any kind of an insult, like say an avalanche or any other kind of disaster type thing. And so that's a big one. And so that requires probabilistic safety analysis for the security and the risk. And then the other one is the materials. We're doing a lot of analysis on the materials because right now we know that what we've described is going to require modifications if we ever get money to do testing, to do empirical testing. We don't think that it would that the burnup would allow the configuration to stay retained within the reactor vessel, because there would be the uranium metal would evolve and it would deform, and that would cause problems. So we're coming up with ways to mitigate that. And that's our next step.
Our next question from Scott. Are you able to sell this idea via a safety perspective through a concept that will allow for staff shut down electrical power production? Then your staff can run away and reactor saves itself.
Yes, we are doing that. And again, I'm not going to disclose the path that we're going because it potentially is proprietary. And if we do choose to patent that, I'll wait until we publish it. But yes, we are considering that, and we do have ideas that we think are robust.
Thanks. Next question from Scott. Are you getting resistance or support from the established nuclear power community? I know the graybeards like to defend their life's work.
Yeah, no support yet. I do have interest from a funding agency that has recently said that they would entertain a proposal. But when I've approached other potential funding sources, I would say this was too novel for most of them.
All right, our next question comes in from John. Is this concept resource limited in terms of beryllium?
Yes. Short answer, yes. There are vendors that provide beryllium, but it's not something that you could suddenly make a large fleet of reactors without having substantial constraint on your beryllium supply.
All right, our next question from Adam. If using only existing UNF from US reactors, are there any guesses to how much UNF you could use per year for, say, 1 gigawatt capacity hyperbreeder?
Read that question again.
If using only existing UNF from U.S. reactors, are there any guesses to how much UNF you could use per year for, say, a 1 gigawatt capacity hyperbreeder?
Well, we haven't done any analysis for recycling used nuclear fuel. That we've considered to be something that would be independent. So once we've burned up our fuel, and let's say we did a fission battery, it would get sent back to the factory, and then we made the assumption that the recycling of that would be an independent organization, facility, capability that would not be something that we're planning for on our own. That's something that we're assuming other people would provide, or the fuel would simply go to a geological repository. That's our assumption at the moment. So we've done no work on looking at recycling other than assuming that smart people someday will bring that about so that we can transfer the fuel and it can be recycled along with the rest of the used nuclear fuel around the country.
Next question from John. If the plates deformed, it reduces the water channel thickness. Are there safety issues?
There would be if that occurred, which is why we're mitigating that. And because I have not published those designs, I'm not going to share that. But that is something we're very well aware of, and that we are making substantial progress in mitigating.
Okay, next question from Scott. What countries have biggest beryllium sources?
Oh, I don't know. I just know that there are vendors. I don't know where they get their ore. Sorry.
Some comments and some compliments in the chat.
Oh, nice.
I do not see any more questions at this time. I'll hold off for a second or two, but in the meantime, I would like to thank Dr. Hayes. This is not his first webinar he's given for HDIAC. So we like to say across all the IACs, we're really only as strong as our memberships and our subject matter experts. So thank you for your time today. Please check back to the HDIAC website. Like I said, the slides are posted there now. Within a couple days, we will have the full recording available as well, so you guys can review the slides. Feel free to contact HDIAC directly at the contact alias contact@hdiac.org. We can put you in contact with Dr. Hayes if you'd like to have any follow-on conversations as well. But this was great. We can tell by the activity in the chat that this was definitely something that was unique and interesting to our membership. So thanks again for the webinar.
I'm here to serve. Have a good day.
All right. Take care, all.